All right, everybody. Today we start a new topic, and it is called hypothesis testing. And this video will just be an introduction to that. There won't really be any math in this video. I just like to get the ideas across to you so that when we do the math later on, that hopefully you understand what's happening, okay? That would be the goal. Now, I want to frame the problem that we're going to try to solve with hypothesis testing before I get into the details of how it's done. Okay? So, I almost forgot. Now, I think I sent an announcement out that before you get started on the assignment I posted on this topic, that you read the book. Okay? So let me just show you about that and what I'd like you to read. So if I'm in my math lab and I go to eText and then I click on eText, then it will open the eText. And let me show you what part of the book I would like you to read in addition to making this video. Maybe watching the video would be enough. But I'm going to at least recommend you read this. I mean, you can do what you want, but that's my recommendation. So we go to Chapter 7, Hypothesis Testing with One Sample. And the video I'm making right now is on this theme, Introduction to Hypothesis Testing. So I'm going to recommend that you read 7.1, all right? Okay, so that's my recommendation, but maybe you might not need to do that if you feel like you understand it from this video. Okay, so here's what hypothesis testing allows us to do. Let's say that some kind of claim is made about a population mean or something like that. So it might be like I always use the same example about the population of house cats. So say there's the population of house cats. Okay, and the claim is that the mean weight of a house cat, meaning the average weight of a house cat, is 7.2 pounds. Like, say somebody tells us that. We say we did a study, and for this whole population, this is the average weight of a house cat. And then I might think something like, well, that seems like a really low average weight. I mean, I think if you average the weights of all the house cats, it'd be a little more than that. Maybe I know something about house cats or something. Maybe I'm a veterinarian, who knows, right? And so I think, could this be correct? Could it be a typo? Could I be misinformed? Did these people do their math wrong? I have all these questions, okay? In the way that we would go about answering those questions and figuring out if this original claim is really true or not is we would assume that it's true. Okay, we'll say, okay, let's say it's true. Let's say the average weight of a house cat really is 7.2 pounds, even though that doesn't seem right. Let's assume it's true. And then we'll take a sample. We'll take a sample from the whole population of house cats. So I might do like this. I might say, all right, I took a sample of 40 house cats, and I found the average weight of that sample to be 9.6 pounds. Okay. And my first thought was, well, that seems pretty heavy in my sample if the average for the whole population is 7.2. Okay, but I guess that doesn't prove anything by itself. Now, then we might do something like this. I think it was for the third test, we learned about sampling distributions. Okay, and you might have to refresh your memory on that a little bit, but let me just get some of the math across to you without you overthinking it too much. The sampling distribution for the sample mean, like this number right here, x bar, has a mean that is equal to the population mean, which we're going to assume is true. We're going to assume that the average weight of a house cat, the whole population, is 7.2 pounds. And then the standard deviation for the sample mean is the population standard deviation, which was given to be 1.4 pounds, over the square root of the sample size, which is 0.22 pounds. Okay. Now, so here's what that means. This number right here, this sample mean, like any number we get from a sample, or almost like any number in statistics, has a certain probability of being what it is. So here's the distribution of this sample mean. Okay, this average weight of the house cats in our sample of 40. It has a mean of 7.2 and a standard deviation of 0.22. Now look at this. There's the mean. Here's one standard deviation above the mean. I just added 0.22. 2 standard deviations above the mean. 3 standard deviations above the mean. And then here's the mean. 1 standard deviation below the mean. I just subtracted 0.22. 2 standard deviations below the mean. 3 standard deviations below the mean. Now, for the normal distribution, it's true that 99.7% of the data is within 3 standard deviations of the mean. Okay? So that means like this number right here, assuming that this number was true, 99% chance, more than 99% chance, is going to be somewhere between 6.5 pounds and 7.8 pounds. What number did we get? We got 9.6, like way out here. So then the thinking is like this. Okay, so if you got lost in a little bit of the math, because it's been a while since we covered this, here's the big thought. Here's the thought that you have. I assumed this was true, and then I got this number from a sample, and then it turned out that number existing has less than a 1% chance. So what's the most rational thought? That you just got this number that has less than a 1% chance by luck? Or that this number was incorrect to start with? What do you think is more true? Are you feeling lucky? Okay, yeah. I would think that yes. I don't think I got this number, this average weight for my sample, by sheer luck, because it has less than a 1% chance of even existing. I think it's more likely that this claim was wrong to start with, whether it was a mistake, whether somebody did their math wrong, whether it was a typo, whatever it is, it's not right. I would reject that that's really the average weight of a house cat. Okay, so that's the kind of the big picture with how hypothesis testing works. Okay, we assume that some given number is true, even though we might not believe it. We take a sample from there, and based on the average that we get from our sample, we actually calculate the probability of that number being true. And, from there, we can judge whether this original number is true or not, okay? Now, it's almost always in math we have to learn vocabulary, and there's not an exception here. So here's the vocabulary for hypothesis testing. Okay, so first of all, a statistical hypothesis is a claim about the population mean. So like above I said, well, I think for the population of house cats, the mean or average weight is 7.2 pounds. But it could be about some other population parameter. You could have a statistical hypothesis about the population standard deviation or whatever. And so, yeah, there's my example is the mean weight of a house cat is 7.2 pounds, or mu, that's the symbol we use for the population mean, is 7.2 pounds. That's an example of a statistical hypothesis. Now, then there's two kinds of statistical hypotheses. There's a null hypothesis and an alternate hypothesis. Okay, so a null hypothesis, we give that the symbol H with a subscript 0, okay? And you could say H0 or H0. Now, the null hypothesis is a statistical hypothesis that involves equality. And what I mean by that is it will involve an equals somehow. So one example, the mean weight of a house cat is 7.2 pounds. That involves an equal sign because we're saying mu, the population mean, equals 7.2 pounds. You see, it involves an equal sign. It involves equality, equals somehow. Another example is this statistical hypothesis. The mean wait time at a doctor's office is 12 minutes or less. How does that involve equality? How does that involve an equal sign? Well, it's equal to 12 minutes or it's less. You see, there's a symbol for that, less than or equal to, okay? So this would be an example of a null hypothesis also. So mu, the mean wait time at a doctor's office, is less than or equal to 12 minutes. Okay, so the null hypothesis might involve an equal sign. It might involve less than or equals. It might involve greater than or equals. But those are the three kinds of null hypotheses that we might have. Now, an alternate hypothesis, and that's indicated by the symbol H with a subscript A, is the complement of the null hypothesis. And by that, by me saying it's the complement, it is what's true if the null hypothesis is not true. Okay, and that might tie your mind in knots a little bit, but we can visualize it, okay? So here's some examples. Suppose that, so here's my first example. So H0 says mu is 7.2 pounds. Suppose that's not true. What would be true instead? That mu is not equal to 7.2 pounds. So the alternate hypothesis is what's true when the null hypothesis is false, okay? Now, sometimes we actually visualize it like this. So imagine like, every population mean is a number. So imagine like this horizontal line is the number line, okay? So I put the null hypothesis in red, that H0 is 7.2 pounds. I put a dot above that. The whole rest of the number line would be the alternate hypothesis, okay? So like here, well, it could be like some number less than 7.2 or some number more than 7.2, but that's just it's not equal to 7.2. Okay, so that's the null versus the alternate in that example. Let's try this example about the mean wait time at a doctor's office. So there, our null hypothesis would be that mu, the population mean, is less than or equal to 12 minutes. So here, I put a dot above the 12 to say, well, okay, the null hypothesis includes 12 minutes, but then I drew a line to the left because it could be 12 minutes indicated by the dot or some number less than 12 minutes, which indicated by the line going to the left, all right? So what would the alternate hypothesis be? Well, if it's not 12 or less, if that's not true, I guess it would have to be more than 12, right? And look at my picture. So I got 12 or less indicated in red as the null hypothesis. And then to draw this line to the right, it would be the alternate, okay? Okay, and then that'd be that mu is more than 12 minutes, strictly greater than. This says mu is less than or equal to 12 minutes for the null hypothesis. This says mu is greater than 12 minutes for the alternate. Okay, so whether you want to think about it strictly in symbols or if seeing a little graph helps you, however you want, you can think about the null versus the alternate hypothesis that way. Okay, so let's see. Now, what is the point of hypothesis testing? Well, maybe you've gotten a feel for this already, but the point is to know the truth. I mean, that's statistics is, or so much of math and science is to know the truth. The way that we come to know the truth is a little bit different in statistics than science or other things, but yeah, we want to know the truth, and you might phrase that in terms of questions. Is the average weight of a house cat really 7.2 pounds? What's the truth? Is the average wait time at a doctor's office really 12 minutes or less? What's the truth about that? Okay, so yeah, we want to know the truth. In the procedure, sorry, that is a cat making all kinds of noise. Anyway, so how is hypothesis? What's the big picture? So I have a flow chart right here for how hypothesis testing is done. Now, I'm not in this video getting into much math at all. I really want this to be about the ideas first, okay? So first we formulate the hypotheses, right? So are we saying like the average weight is 7.2 pounds or not, right? Then we take a sample from the population because the hypotheses are going to be about population parameters such as the population mean. So we take a sample from the population, we calculate the sample mean known as X bar or S, the sample standard deviation, as needed, okay? Then we perform statistical tests, and we will get into the nature of those statistical tests in the next assignment and the next video. Then, based on those results, we decide to accept or reject the null hypothesis. Okay, so that's the flow chart. You know, the first part's probably not that hard. Taking the sample and doing the calculations probably isn't that hard. The statistical test might be the challenging part, and then making your decision is probably not that hard, okay? But that's the flow chart. That's how it's going to go. Now, last question. Can hypothesis testing ever be wrong? I don't know what that cat's trying to do over there, but I wish she would come on camera so you could finally see her. But anyway, can hypothesis testing ever be wrong? Well, of course, like, yes, I mean, because it's done by humans and we can be wrong. But the reason why hypothesis testing can be wrong sometimes is we decide to accept as true or reject the null hypothesis based on probability. It's all done based on probability. So like up here, I could say, remember this example where I said, I don't think the average weight of a house cat is 7.2 pounds. I think that that was a mistake or bad information or something. And the reason why I think that is because the sample mean I calculated had a probability of less than 1%. So that's why I would reject this. But does that mean I'm absolutely certain to be correct in rejecting this information as false? I mean, if I say this sample mean has a less than 1% chance of being legitimate, well, that means there's a possibility that it could be legitimate, all right? It's not very likely, but yeah, so, you know, that, like there's a less than 1% chance that I reject this number as a mistake, and I do so wrongly, okay? And I'm incorrect in rejecting it. It's just not very likely. All right. So yes, for sure, hypothesis testing can lead you to make the wrong decision, and you can be wrong, and there's always a small probability that that happens. Now, the statisticians have very, very creative names for the types of mistakes that you can make in hypothesis testing, and I say that totally sarcastically because they call the mistakes type 1 errors and type 2 errors. But okay, it's part of learning hypothesis testing is knowing the types of mistakes. And it's not like I even expect anybody who learns statistics to remember this. I don't walk around remembering what a type 1 error or a type 2 error is. I know that one is here and one is there, but I can get them mixed up. Okay, I mean, in principle, I understand what they are, but it's not like I've memorized them and I just walk around all day knowing it. But so, okay, have this chart handy or you're like in your notes or something. So let's divide this up. You make a decision to either accept or reject the null hypothesis. And the reality is that the null hypothesis is either true or false. Okay, so there's your decision versus reality. So look at it like this. If you decide to accept the null hypothesis as true, and the null hypothesis is actually true, well, then you're correct. And if you decide to reject the null hypothesis, and in reality, the null hypothesis is actually false, well, then you're correct there. Okay, where the mistakes come in. that you accept the null hypothesis as being true, but the null hypothesis is actually false. That's called a type 2 error. I'm sorry. And then suppose that your decision is to reject the null hypothesis, but in reality the null hypothesis is true. Well, then that would be a type 1 error. So those are the two ways that you can make a mistake in hypothesis testing. So all right, it's all in that chart right there, but I thought, let's do one example. So suppose H naught, null hypothesis, the mean weight of a house cat is 7.2 pounds. All right. And alternate hypothesis, mean weight of a house cat is not 7.2 pounds. Okay, suppose I decide, based on all these statistical tests I did, to reject the null hypothesis, but later I learn that it really is true that the mean weight of a house cat is 7.2 pounds. Which type of error would that be? That would be a type 1 error, right? Because I rejected it, but the null hypothesis was actually true. Yes, type 1 error. I can admit my mistakes, right? I knew it's possible that I could make a mistake when I do hypothesis testing. Okay, so I hope that you find everything you need in the video, but it might be that there's a few small details left out. So that's why I asked that you read 7.1 of the book. I mean, I think the book is pretty good and complete. I think it's fairly easy to read. But how about this? Try to read the book, and hopefully you've watched the video up to this point. And then when you work on the assignment linked to this video, if you're having trouble, you can always ask for help. I can make another video with more detailed information. I would just need to hear from you if that needs to be done.